Everyone. I am Payal Singh, Assistant Professor from ASH Department. I welcome you all on the behalf of Parul University. Today we have our guest Dr. Vinod Kumar Gupta from DIT University, Dehradun. He obtained his Master of Arts from Banaras Hindu University, Varanasi in 2006 and PhD in 2014. He has also qualified GATE 2009. He is having several international research papers in the field of fluid dynamics. He is also serving as a reviewer of many international journals like Physics of Fluids, International Journal of Heat and Mass Transport, Journal of Porous Media, and many more. He is also an active member of Ancient Council of Science, Editors Dubai. Now I request Dr. Vinod Gupta. Sir, please start your topic, and this topic is on application of fluid dynamics.
Thank you. First of all, thank you to Dr. Pal Singh for inviting me and her entire team. Today's topic is application of fluid dynamics in day life. So how we use the fluid dynamics in our day-to-day life. So let me share. So this presentation contains first of all the preliminaries about the fluid dynamics. We will talk about the basic concept of fluid dynamics, and after then, how we will model them, the mathematical modeling of this fluid dynamics and their interpretation and conclusion. So first of all, we will know what is the fluid dynamics. Fluid mechanics is the branch of science which deals with the behavior of fluid at rest as well as in motion. So basically, we will analyze the dynamics of fluid. So the fluid dynamics can be divided into three parts, as you have studied in graduate level: hydrostatic, kinematic, and dynamics. So hydrostatics is basically, in that hydrostatic we deal about the mechanics of fluid at rest. Right? So because there is no motion, we will study the hydrostatic motion. And kinematics, in kinematics we will deal the properties of fluid with this rotation, deformation of fluid. And here we will not consider any external forces. External forces we will not consider the rotation. Rotation is the body force. You may consider this rotation, electromagnetic force, right, and gravitational force. All these are under the body force. We will not consider them in kinematics. In dynamics, we will consider all of them. So we will study the behavior of fluid, velocity, acceleration, right, under the forces which exerted on the moving fluid. So further, we will see what is fluid. So matter exists in two principal form, as we know. The matter exists in the universe, that is in two-step form, that is solid and fluid. We have not considered here the plasma, solid and fluid. Further, fluid can be divided into sub-parts. So in fluids, we will consider the gas and liquid. Fluid means liquid and gas. So in fluid dynamics, basically, we will study the behavior of liquids as well as gases. So first of all, we will see what is the application of fluid dynamics in our day-to-day life. So first of all, let us see that. So when we wake up in the morning, right, then you see the coolant circulating inside it, and the cool air which it gives is the fluid. because as we have seen earlier that fluid means liquid as well as gases. So when you start the AC, there is a mechanism which is based on the fluid dynamics. So here we use ramped temperature. Ramped temperature means after a certain time, the temperature will be depends on time, and after arriving that temperature, it will cool down. That it will be constant. So that is the application of ramped temperature in AC. The next, when you work in sink, you see the flow of the fluid. Right? That is due to the atmospheric pressure. So that is also a application of fluid dynamics. And after that, you decided to have a breakfast. After breakfast, if you see the fridge, right, when you open the door, a cooled air is passing out, right? That is also an application of fluid dynamics. Because in fridge, there is a mechanism of fluid dynamics because it's coolant property. And this compressor, the flow of fluid due to the pressure term. And this is the cleaning process. When you go for the cleaning, so we will use here the suction, right? Because the suction process is there. And another example of fluid dynamics in here involves right? How we should design this, it will flow in water, right? That is again a property of this fluid dynamics. And the fuel, the mixture of fuel like petrol and air is caused by atmospheric pressure, right? And nowadays there is a inject property, right? That is the one of the application of a droplet. But nowadays, if you see in bikes, uh, they use the inject property of fuel. So that is one of the application of a droplet. And again in inkjet printing, there is again application of fluid dynamics. So these are the significant applications which we use in daily life. So basically, I work on the stability of the fluid. So first of all, let us see what about the stability. So there are two forms of atmospheric stability. One is convective, and another is dynamic. That is the fluid mechanics. So I work on this convective instability. We will deal that. This is the problem. See how we will define the stability. The first one, this is the diagram of laminar flow. A flow is said to be laminar if it moves on a definite path on a parallel line. Means the adjacent fluid particles do not intersect each other. So that is called the laminar flow, and it is called the stable. And this is the turbulent flow. If the path of the fluid is not definite and it is intersecting path, then it is called the turbulent flow. The turbulent flow is known as the unstable state. So we will talk about the stability, then we will see the laminar flow. And after then we will talk about the Rayleigh-Benard convection. So first of all, we will see what is the Rayleigh-Benard convection. So Rayleigh-Bénard convection is the type of natural convection. So we see what is the natural convection. If you see on the top of a T, if you are heating, then it is a natural convection. But to increase the heat process, if someone starts the fan, that is called the forced convection, because you are regulating externally by the fan. So that is called the forced convection. So we will deal only by the natural convection. Natural convection means convection is stuff without any external forces. So Rayleigh-Bénard convection is a type of natural convection occurring in a plane horizontal layer heated from the below, and which to develop a regular pattern of convection cells, and these cells are known as Bénard cells. So when you heated this fluid from below, the cell will be started, and that cell is known as Bénard cell. Like this, if you see this cell, when you heat this from below, the formation of cells is here. So these are called the Bénard cells. And next, that is the Q theory. Q theory is also a branch to determine the stability of the system. The Q theory, that is observing weather. First of all, the Q theory in fluid dynamics, it is used by the Lorentz, a meteorologist, in 1963. So he has used this fluid dynamics to predict the weather forecasting. So first application of Q was there. So Q theory is used in many branches of engineering science, in geology, mathematics, microbiology, mathematical modeling. In fact, in today's era, in COVID-19, Q theory is also used to determine. So first of all, we know what is the Q theory. What is Q? If you see from the picture, in picture behind, the children are fighting to each other, and someone expects what we have to do. Right? So that position is known as the cure. Right? If we are not in position to guess what has to be going on, so that step is known as cure. And next, there are several paths. We cannot determine where we have to go, what path we have to choose. So that stage is also cure. And suppose you are in the traffic. In this traffic, if you are not determining where we have to go, so this situation is also known as the cure. Cure is the state where we cannot predict the motion of fluid or anything, right? Unpredictable behavior, that is known as the cure. And that's about the day-to-day life application of fluid dynamics. Now come to the topic. So first of all, we will classify the fluid. So there are two types of fluid. One is Newtonian and another is a non-Newtonian fluid. So a fluid is said to be Newtonian if the stress is proportional to strain rate at any point of the fluid, where this tau is the stress rate, mu is known as the dynamic viscosity, and du over dy, that is the rate of strain, means the velocity gradient in perpendicular direction of the fluid. Right? So if we find here tau over du over dy, that is mu, and mu is constant, that is called the viscosity of the fluid. If the fluid obeys this rule, then we will say the fluid is Newtonian. Or in another way, you can say, if the fluid is independent of stress rate, then we will say the fluid is Newtonian. Otherwise, we will say it is non-Newtonian. So some example of a Newtonian fluids are here: alcohol, motor oil, that's not crude oil, that is the motor oil, water, and gasoline. These are some examples of Newtonian fluids. And the non-Newtonian fluids are fluids which do not obey the Newton's hypothesis of Newtonian fluid, that is called the non-Newtonian fluid. For example, that soap solution. Right? So first of all, we will also see what is the stress. Stress is the when a force is applied to the fluid, then its tangential component is known as stress, and the normal component is known as strain. So stress is basically works in the direction of tangential when the fluid is flowing. Then the force between two adjacent layers of the fluid is called the stress. Right? Toothpaste, that is also non-Newtonian fluid. In fact, we say this is the plastic fluid. Toothpaste, you know, this is also as a gel, but basically it is the plastic fluid. What is the plastic fluid? Is a fluid which flows after applying the stress. Because if you see the toothpaste, when you squeeze from the bottom, the toothpaste come out. Means when you apply the force in tangential direction, the toothpaste will flow. So that is known as the plastic fluid. That is the category of plastic fluid. Cosmetic, that is also a non-Newtonian fluid. Butter is also this non-Newtonian fluid, because when you see the butter, viscosity is very high. Right? Means tangential force between two layers is very high. That's why it will not flow automatically without applying the tangential force. Now we will see what are the governing equations of fluid flow and heat transfer. Right? If fluid is flowing, then there will be automatically Newton's law of motion. Right? So there are some assumptions for the fluid flow. The first is the mass of fluid is conserved. This is also known as equation of continuity or mass conservation law. The second assumption is the rate of change of momentum equals to the sum of the forces acting on the fluid particle. Because if the fluid is in motion, then there will be Newton's second law of motion will work, and it says that the change in momentum is equal to the sum of all forces acting on the fluid particle. And third one is corresponding to heat transfer, because if you are heating the fluid from below, it means that you are increasing the temperature of fluid. That is based on the first law of thermodynamics. The rate of change of energy is equal to the sum of the rate of heat addition to and the rate of work done. Because if you add the heat, then there will be some work done. Because you are adding the energy, then there will be some work done. And you can also see in daily life, right? Because if you have the energy, then you will do the work. Right? Suppose you are sitting, then you feel after 2 to 3 hours that you are tiring. Why? Because there is also an application of fluid dynamics. Because on your body, the gravitational force and the atmospheric force are acting, and you are balancing them. To balance them, you are wasting your energy. That's why you tired after 2 to 3 hours. Right? You see, you are not working anymore. So that is also application of fluid dynamics. So there are certain rules to analyze the stability of this fluid flow. One is the energy method. So in energy method, you will write the kinetic energy of the system. And you can see from the nature, if you have energy, then you will be unstable. Because if we have the energy, then we will move down here to there. If we don't have energy, then we will not move. We will sit. Right? So it means that if the energy is dissipative, means if energy is decreasing with respect to time, then our system will be stable. If the energy is increasing, it means that the system is unstable. So that is one of the methods to check the stability of the system. So these are the basic laws which work in the fluid dynamics. If there is any fluid flow, then the fluid must obey these three rules, right? If there is any other solute concentration, then there will be one more rule for the solute concentration. So first of all, we will talk about what is the continuum hypothesis, because when we go for the model, we want to model this flow of the fluid, right? So that will be in terms of derivatives. That will be in terms of derivatives, right? So first of all, we will talk about its differentiability. Can we differentiate this? Right? So you know the differentiability. So for it should be continuous, right? So that is the continuum hypothesis. If the distance between any two fluid particles, that is 1 micrometer or greater, right? Then we will assume that the fluid is continuum, and we can talk about its continuity and differentiability. Right? So that is the continuum hypothesis. So we will see the first mass conservation law, because if the fluid is in motion, then we have seen here, the first is mass of fluid is conserved. So, right, so we see what is the mass conservation law? The rate of increase of mass in the fluid element, that is equal to net rate of flow of mass into fluid element. Means the mass entering from one region, that should be equal to the outflow of the mass. So that is your equation of continuity, and that is also known as the mass conservation law. So when you form this will be here del rho over del T, where rho is the density and vector Q is the velocity of fluid particle. So del rho over del T plus this divergence of rho dot vector Q, that is equal to 0. Right? So that is the equation of continuity. And when fluid is incompressible, incompressible means the density does not depend on the temperature as well as time. The density is independent of this temperature. Right? So gases are compressible because when you increase the temperature, right, it will be damped. The fluid is in. So if you assume the fluid is incompressible, then rho will be treated as a constant because there is no variation in density, and your equation will be turns out is del dot Q equal to 0. Apparently you use in this the divergence of vector Q is 0, right? So that is the mass conservation law. And the next momentum equation, that is based on the Newton's second law of motion. As you know, the Newton's second law of motion, it states that the change in momentum, that is equal to the sum of all forces acting on the fluid particle. Right? So by that we can write rate of increase of momentum of fluid particle, that is equal to sum of forces on fluid particle. So what now we will see what are the forces acting on the fluid particle. If fluid is confined between two horizontal layers, right? Then there will be the pressure term and this gravitational force. So pressure, that is your body force. Pressure is the surface force and this viscous force. This mu is corresponding to viscosity. So del dot P, that is the pressure term, and this mu del square Q, that is the viscous force. So these two are the surface forces, and the rho vector G, that is the body force, which acts on the body. Right? So this left hand side, we can write this capital D over dt. So capital D over dt, that is the change in the fluid element. How we can write this? Del over capital D over capital dt, that is equal to del over del T plus Q dot del. Right? So we can see how we can define this. If you see the Lagrangian, and let phi be the any state. Let me show you. That is if you define this u in Lagrangian, you will define here this u is a function of this t, x, y, and z, where this t, x, y, z, that is also a function of time. So when you find here du by dt, then you will see that is nothing but that is your partial del u over del t plus del u over del x into that is your partial of this is partial of del u over del t and plus again this is here del u over del t into del x by del t. Right? When you expand this by total differentiation, right? So you will get here del u over del t plus again this is here partial derivative of u with respect to t to dx by dt plus again del u over del t into del y over del t plus del u over this del t plus del z by del t. And since x, y, z, this is these are the spatial coordinates, so the value of this del u over del x, right? Du dx by dt, that is the x component of velocity, and this dy over dt, that is the y component of velocity, and dz by dt, that is the z component of velocity. So we have used it here, right? So when you use here, you will get its value, that is del over del t plus when you expand this vector q dot del, you will get here u del over del x plus v del over del y plus w del over del z, and that is equal to equivalent to Lagrangian of that. So suppose our fluid is in a rotating machinery, then there will be one more term here, right, in right hand side, because that is also a body force. So one more term is here if the fluid is in rotating. And suppose the fluid, we applied here a magnetic force, then we will get a next term here, electromagnetic force here, because it states that the change in momentum that is equal to sum of the all forces acting on the particle. Right? So Navier-Stokes equation will be changed according to situation, what type of problem you have considered. On left hand side will be remain same, the only change will be here, right? Depending on the rotation, depending on the electromagnetic forces, so right hand side will be changed. And the next is the energy equation. The energy equation is based on the first law of thermodynamics, and which states that the rate of change of energy of a fluid particle is equal to the
Sir,
rate of heat
please use
addition.
full screen.
Okay.
Huh. Thank you, sir.
So this states that the rate of change of energy of a fluid particle is equal to the rate of distance of the fluid particle plus the rate of work done. So again, here, capital D over dt of T, right? If you define here earlier, here, this capital D over capital dt, that is nothing but del over del T plus Q dot del. Right? If you apply here on temperature T, then it takes the form del capital T over del T plus Q dot del, and it is here T. So that is in here. The rate of increase of energy of fluid particle. So that is capital dt over dt. Right? This is small t. That is with respect to time, and capital T is with respect to the temperature. And that is equal to the net rate of heat addited to fluid particle, that is here. Because the value of net rate of heat addited to fluid particle, that is equal to minus divergence of Q. And according to Fourier heat conduction law, the Q equal to minus time of kappa gradient of T. That is the relation between the temperature and the velocity of fluid particle, that is given by the Fourier. So according to that, it will be converted into here del dot, that is the divergence of K grade T. And that is nothing but the minus time divergence of Q. The actual expression is the net rate heat addited to fluid particle is minus divergence of Q. And the value of Q is minus time of kappa grade T according to Fourier law. So we have used the first law of thermodynamics given by the Fourier. So these are the basic equations for the fluid flow. First one is the equation of continuity, that is the mass conservation law. Second one, that is the momentum equation, that is also known as the Navier-Stokes equation. And third, that is the energy equation. These three basic equations will be used in a Rayleigh-Bénard convection. Right. So let us explain this by some problems. Right. So we have done some problem on the gravity modulation. I have considered here the gravity is time dependent, it's not constant, and you can experience this gravity modulation, right, in the sound of a rocket for a long time, right, and in extended stay of orbit, and the drop of a tower. Right, when your tower is dropping, you will experience your gravity is decreases for a very short time. So this gravity modulation is worked for a very short time. It is also very useful in establishing a laboratory in space, because nowadays we are seeing that many countries are establishing their laboratory in space. So first is established by the China. So there it will work because their gravity is not constant. So let me explain what is the formulation this is. So we have taken a fluid layer, that is the at this depth d apart. The lower plate is along x-axis and upper plate is along z-axis. And this and infinitely extended in x direction. Fluid is saturated between these two layers, and gravitational force vector g equal to minus time g, because why we are writing here minus g naught, because the z positive direction of z axis is in upward direction and gravity is working in the downward direction. So that's why vector g is minus of g0 1 plus epsilon square delta cos omega t. So that is here modulated term. This delta is amplitude of modulation, right? And since we have considered the modulation is periodic, so that's why we have chosen here the term cos omega t. and an applied magnetic field H naught that is applied along the z direction. When you apply the magnetic field, it will create a magnetic force on the fluid particle, right? So in this situation, our governing equation will be this, right? So first one, that is the equation of continuity, del dot vector C, because we have assumed that fluid is incompressible, right? So fluid is incompressible, then equation of continuity takes this form. This is corresponding to the magnetic field, vector H denotes the magnetic field, del dot vector H. That is the conservation of magnetic lines, right? So conservation of magnetic lines states that the magnetic lines enters through a region that is equal to the magnetic lines outside the region. जितना inflow होगा उतना ही outflow होगा, that is corresponding to equation of continuity. And this is our momentum equation, right? We see here left hand side is remain same. This is the change in momentum, and that is equal to sum of all forces. So when we talk about this is the pressure term, that is the surface force. This is the gravitational force. In the place of vector g, we have written its value, that is minus of g0 1 plus epsilon square. And there is the mistake we have taken here delta, right? So it should be here delta cos omega t. Plus this is the viscous force, and this is the Lorentz force. Because when we apply the magnetic field, there will be magnetic force will be generated, right? So according to Newton's second law of motion, the change in momentum that is equal to sum of all forces acting on the body, right? And that is here the equation for concentration, because we have used the solute concentration. And this equation is corresponding to magnetic lines. And rho equal to rho naught 1 plus beta s minus s naught. That is known as the Bondsnet Approximation. The Bondsnet Approximation states that rho will be constant, density will be constant throughout the motion except the equation of motion. Right? This is also known as the equation of motion. So it says that this density varies with respect to temperature and initial concentration. So when you increase the concentration, density varies, it will increase. If suppose we have taken here temperature, then it will be one more term here, minus alpha T into T minus T naught. Because when you increase the temperature, density will be diluted. And soluble boundary condition, so we have taken the concentration at this lower plate, S equal to S naught, and upper plate, S equal to S naught plus delta S. And the concentration at upper plate is higher than the concentration at lower plate, right? Then a concentration gradient delta S will work across this depth D, and due to that, the convection will start. Soluble convection will be start. So now we process the instability. So first of all, we know how we have to process it. So what we will do for the stability process, so let there is a stable system. So what we will do, we will create an infinitesimal disturbance in the system. If this disturbance dies out with respect to time, then we will say our system is stable. And if this disturbance grows out with respect to time, then we will say our system is unstable, right? So first of all, we will create a disturbance in the system. So for that, this is our basic state. Basic state that is also known as the equilibrium position, right? Because we will check the stability of a stable system. If the system is stable, then we will create a small disturbance in the system, and we will check its impact, so whether this small disturbances dies out or grow. So we have taken the velocity fluid is at rest because our system is stable, so we have assumed fluid is at rest, so velocity is 0. Pressure is the only function of jet in only z direction. Concentration, that is only the function of z. Why the function of z? Due to this concentration difference. Lower plate concentration is S equal to S naught, and the concentration at upper plate, that is equal to S naught plus delta S. Right? So the transfer of concentration will be only vertical direction due to the difference of pressure at these two boundaries. And rho equal to get a function of that. So when we substitute these values in governing equation here, we will get the differential equation says kappa del square f b over del z square equal to 0, and del p b over del z equal to rho b into vector g. You can write the value of vector g here. When you solve this equation, you will get SB equal to AZ plus B, and we will apply the boundary condition that S equal to S naught at Z equal to 0, and S equal to S naught plus delta S at Z equal to D. So from there, when you use the boundary condition, you will get the solution of this differential equation 9, and that is given by SB equal to S naught plus delta S into Z by D. And after then, we will create a small disturbance in the system. So for that, we perturb this S equal to SB plus S dash, method deviation from the basic state, that is your equilibrium position, Q equal to QB plus Q dash. So this S dash, Q dash, P dash, H dash, and rho dash. These are the small disturbances in concentration, velocity, pressure, and magnetic forces. And now we will check their impact on the system. And after then we will perform the non-dimensionalization process, because if you see in equation, the dimension of each term are different. So before solving these equations, first of all, we will non-dimensionalize these equations by these parameters. So when you substitute these values, we will get this set of partial differential equations. We have size the stream function, right? Size the stream function, and that is defined by u equal to del psi over del z, and w equal to minus del psi over del x. And this phi is the potential function, and we again define the x component of magnetic force, that is equal to del phi over del z, and the z component of magnetic force, that is hz, that is defined by minus del phi over del x. So we introduce these two variables. So we write our equation in terms of the psi and phi instead of q and h. Right? So when you write the value of q, vector q equal to what? U v w, and we replace the value of u by del psi over del z, and the value of w by minus del psi over del x. Right? And this j is stand for the Jacobian of psi comma s with respect to xz. And these are the boundary conditions. So as you know, the cells are periodic. So we will assume our solution in periodic form, right? So for the nonlinear stability analysis, we have assumed this tau equal to epsilon square t, because when we experience the gravity modulation, time is very short, right? So that's why we will rescale this tau equal to epsilon square t. So when you substitute an equation, you will get this set of equations. Now we have to determine its solution. To determine its solution, we have used here series solution, and that is also known as the asymptotic analysis method. So we have expanded this, our variables are here, psi, s, phi, right, and this RAS. So we will expand these variables in terms of series, right? And for the convergence of this series, we will choose the parameter epsilon that is very less than 1. That is less than 1. Very small quantity. Right. So what we will do, we will substitute the value of psi s, phi and RAS in these equations and equate the similar terms of at various orders. Because if you substitute its values psi s, phi and RAS in your equation, you will get the terms of psi square, right? We will equate them on both sides, and that gives a solution at different orders. So when you equate these, this is first order solution. First order solutions mean we will equate the coefficient of this epsilon on both sides. When you substitute this value, and after substituting these values, we will equate the coefficient of this epsilon on both sides. Then that gives you the set of this partial differential equation. And you know that these cells are periodic. So cells are periodic. So we will assume this psi s and phi in the periodic form. You can also refer this by the Fourier series method. Right? So Fourier have initially solved the heat and wave equation, and he found that solution is in terms of the sine and cosine. Right? So we will choose this, satisfying this boundary condition. Boundary condition is here. That is on the bottom. Psi equal to 0 at z equal to 0. And psi equal to again 0 at z equal to 1. So we will consider our solution which satisfies this boundary condition. That is also heat and trial method. That is not sure if that will be solution. You may consider different solution which satisfies this boundary condition. This is that. When you substitute here x equal to 0, you will get psi 1 is 0. When you substitute z equal to 0, this is again. So this will satisfy the boundary condition. So we have assumed one of the solutions is in the form of this. A tau, B tau and C tau. After that, we will substitute the value of this psi 1, S1, phi 1 here. And that gives the value of B tau and C tau in terms of A. So the only unknown is A tau, which we have to determine. If we can determine the value of A tau, then we have the expression for this psi, s and phi. So we will determine its value in later stage. And from there, we can also get the value of this critical solute Rayleigh number. So let me see what is the critical, first of all, we will know what is the critical thermal Rayleigh number. So this RAT. This thermal Rayleigh number is ratio of buoyancy force to the viscous force. Because when the fluid layer is heated from the below, a temperature difference due to the temperature difference between the boundaries, convection will start. And buoyancy forces comes into the picture. If the buoyancy force is greater than the viscous force opposes the fluid's motion, right? And buoyancy force drives the motion. If the buoyancy force is greater than the viscous force, that is Rayleigh number is greater than 1, then the convection will start. So this is this RAS, that is the solute Rayleigh number. Why we are using a solute? Because we have not taken the temperature in our problem. I am working only with the concentration, so that's why we name this solute Rayleigh number. If you work with the temperature, then there will be the term thermal Rayleigh number. The rule is the same. So this is the critical value. Beyond this value, convection will start. Right. So RS net means we are in equilibrium position if it is equal to this. Beyond this value, convection will start. When the process of mass transfer will take the place. This Q is the Chandrasekhar number. Chandrasekhar number is corresponding to this Lorentz force, right? Because we have applied the magnetic field, so this Q will come into the picture. That is the Chandrasekhar number. And for the second order solution, we will equate the coefficient of epsilon square on both sides, and that gives the system of differential equation, where the right hand side is defined by this, right? R21, R22, R23. And that is in terms of psi1, phi1, and s1. And now we will substitute the value of psi1, phi1, and s1 from the previous. You have already assumed that here, psi1, s1, phi1 is. We will substitute its value here. So that gives you the value of R21, R22, and R23, and we will write this in equation form, right? And from there we will obtain its solution. So when we will write and compute, since the boundaries are isothermal, so we will get psi2 equal to 0. And when we substitute psi2 equal to 0, why we are setting psi2 equal to 0? Due to the isothermal condition.
Sorry to disturb you, sir. You have 10 minutes to conclude.
Okay, okay. And this is the, similarly, we will find this third order solution. Third order solution, we will equate the coefficients of this epsilon cube on both sides. So that gives you the third order solution. And after then we will apply the solvability condition, and which gives a differential equation in terms of capital A, which was needed at the first order. So from here we will obtain the value of this A tau. So this is the first order linear differential equation, right, which is reducible to linear differential equation. And the only difficulty is this time dependent coefficient. We have already studied the Bernoulli differential equation, right? So in there, that depends only on the x and y, that is not dependent on independent variable. So this is this time term, right? So it is difficult to solve analytically. So for that, we will take the help of RK4 method to solve this differential equation. And this mass transfer that is computed by this. This is square root number that is corresponding to mass transfer. Right? It will tell how the mass transfer is taking place. So that is equal to 1 plus kc square by 4 delta square E square tau. And A square tau, A tau can be obtained from the previous differential equation. After substituting its value, we can determine the value of square root number. And these are some graphs. So this is about omega equal to omega. Omega is the frequency of modulation. So we see that if the frequency of modulation is increasing, the amplitude of this transfer, right, it is with omega. It increases the mass transfer, so it will decrease. So the system is unstable. Next, this is the Smith number. So when we see here, when we increase the value of the Smith number, again the mass transport increases. Right? So it will also destabilize the system. And all of the graphs are computed on Mathematica. And that is the magnetic Prandtl number. So if you see, the similar type of variation is also in PM. So when you increase the value of PM, the value of this square root number is increased. So this also have the destabilizing nature. So these are some effects of this Cherenkov number, magnetic Prandtl number, and the frequency of modulation on the system. So whether they will increase the mass transport or whether they will decrease the mass transport. Right? Accordingly, we will choose their values in our practical problem. So these are about, and thank you to all.
Now, I would like to request to all the participants to ask questions if they have. Okay, I think there's a no question. Sir, I have one question. How you are
Okay.
selecting the parameters when you formulate such kind of partial differential equation? Is there any restrictions applied on these parameters?
Okay, but means you are asking about the range of parameters. See how we have chosen the value of Q,
Exactly, sir.
Pm. Yes,
Yes,
okay.
sir.
Okay. So if you see the definition of these parameters, this Pm, let me show the slide. From here, you can see here.
Yes, sir.
This is about the viscous force, magnetic force divided by viscous force. So we have, if Q is greater than 1, it means that magnetic strength is greater than the viscous force. So
Okay.
accordingly, we will choose this value. And Pm, this is magnetic diffusivity divided by solute diffusivity. Right? So accordingly, from here, we will choose its value. For example, this is a Sp, that is the Smith number, that is the kinematic viscosity divided by this solute diffusivity. If the kinematic viscosity is greater than solute diffusivity, what is the nature of the system? Right? So we
Okay,
will
sir.
choose its value from here.
Okay. And sir, the same thing we do for the boundary conditions that we take. Boundary.
Boundary condition that depends on the nature of the boundary. We have assuming here the no slip condition. According to that, we will choose the boundary condition.
Okay. Okay. You have taken here s equals to 1 and z equals to 1. So there is some specific reason behind it.
What s equal to?
1 at z equals to 1. Initially, both are 0 and then you
Okay,
take 1.
okay. From we have chosen its value from here. So when you transfer S naught this side, SB minus S naught. And if you see the perturbed quantities, SB minus S naught, that is your S dash, perturbed quantity. So when
Okay,
you
sir.
perform the non-dimensionalization, S dash will be Z.
Okay,
Right?
sir.
So
Okay.
from here, right, when you substitute here Z equal to D, it will be 1.
Okay, sir.
Yes.
Got it. Thank you so much, sir. And again, I want to say thank you on the behalf of ASH department from PIT and PIET and the Parul University for sparing 1 hour and giving us the knowledge about the fundamental things about the fluid dynamics. Thank you so much, sir.
And thank you to all.